Hello and welcome to this revision session on particle physics for AQA A-level physics. So in the first part of this revision session we're going to be looking at the constituents of the atom. So we can represent an atom of element X in the following way. Now in this notation, Z is the proton number, so it's the number of protons in the nucleus. Now an uncharged atom will have the same number of protons as it does electrons. Now in chemistry we call this the atomic number. Now A in this notation is called the nucleon number, or in chemistry it's called the atomic mass number. Now this is the total number of nucleons, so protons and neutrons in the nucleus. So we can work out our number of neutrons, the neutron number, by doing the nucleon number minus the proton number. Now this is the extent to which particle physics was covered at GCSE. Now one method of differentiating between particles is by measuring the mass. However, our issue is that the SI unit of mass, the kilogram, can be difficult to work in for particles. So instead we use the mass energy equation to derive a more workable unit for particle masses. Now the unit of mass most commonly used in particle physics is called the mega electron volt per speed of light squared, or MeV over c squared. Now MeV over c squared is not an SI unit. Now the MeV over c squared is an easy unit of mass to mathematically manipulate. However, if you wish to determine another SI unit, so for example meters or a derived unit such as hertz, it's got to be converted back to kilograms. Now our conversion factor is that 1 MeV over c squared is equal to 1.78 times 10 to the minus 30 kilograms. Now another unit of mass which is used by particle physicists is the atomic mass unit, which is the unit of particle mass used at GCSE physics. So one unified atomic mass unit is approximately the mass of one nucleon, so either a proton or a neutron. So we define this as 1/12 of the mass of an unbound neutral atom of carbon 12. Now we know that 1 U is equal to 1.661 times 10 to the minus 27 kilograms. So to convert from your non-SI units into your SI units, you've got to multiply by the conversion factor. So you've got to be able to convert from MeV over c squared into kilograms and from U into kilograms. But you've also got to be able to go the other way around. Now again, just remember before we look at this, MeV over c squared are units of mass derived from the E equals mc squared formula, whilst the simplified units of mass are used in previous topics. So for example, we would say that protons have a mass of 1 U. Now you can see here, to convert from an SI unit, your kilograms, into the non-SI units, MeV over c squared and U, you've got to divide by the conversion factor. Now another idea we've got to understand about particles is the idea of charge. Now at GCSE we stated that particles were either positively, negatively or neutrally charged. So we would say they'd have a charge of +1, -1 or 0. Now there were no units to this, it was a relative charge of the object. Now we've got to now in A-level physics express charge in terms of coulombs, the SI derived unit of charge. So we can no longer say the electron has a charge of -1 or the neutron has a charge of 0. Instead we've now got to use charges in terms of coulombs. Now 1 unit of relative charge is equal to 1.60 times 10 to the minus 19 coulombs. So the proton has a charge of +1 or plus 1.60 times 10 to the minus 19 coulombs. The electron has a charge of -1 or a charge of minus 1.60 times 10 to the minus 19 coulombs, whilst the neutron has no charge. Now you should memorize this value for your understanding moving forward. Now for particles, to find a more useful quantity than charge or mass is in fact the charge to mass ratio. Now this is called the specific charge of the particle. Now the specific charge influences the particle behavior because the specific charge details how much a particle is deflected when it is inside an electrical field. So the larger the specific charge, the greater the deflection. The smaller the specific charge, the lower the deflection. If an object has no specific charge, it will not deflect in an electrical field. And the same is also true for magnetic fields. So the larger the specific charge, the greater the deflection in a magnetic field. The smaller the specific charge, the lower the deflection in a magnetic field. And if the object has no specific specific charge, it will not deflect in the magnetic field. So how do we calculate specific charge? Now in physics, specific means per kilogram or per unit mass, so therefore specific charge is the charge divided by the mass. Now we have our charge in coulombs, our mass in kilograms, so our specific charge is coulombs per kilogram, and the specific charge of the particle indicates how much it will deflect in an electrical or magnetic field. So like we said before, the larger the specific charge of a particle, the greater the deflection of the particle in an electrical or magnetic field. But please be aware this equation is not given to you in the equation book, rather you've got to memorize it yourself. So what you would do to work out your specific charge is you work out your overall charge in coulombs and divide it by your overall mass in kilograms. Now it's important to note that as specific charge is a scalar quantity, a minus sign is not required. Now for an ion, remember that the mass includes both protons and neutrons, but you don't need to add the electron mass because it won't affect your answer to the significant figures that are given. So as ions contain neutrons, like we said before, they'll contribute to the mass but not the charge. The specific charge of an ion is much smaller than that of a charged particle. Let's now have a look at the concept of stable and unstable nuclei. Now we learned in GCSE that the atom is predominantly empty space. The radius of an atom is about 10 to the minus 12 meters, and the radius of a nucleus is about 10 to the minus 15 meters. So this means that the radius of the atom is about 10,000 times bigger than the radius of the nucleus. Now the reason why this is the case is that the electron cloud repulsion and the proton-proton repulsion means that the atoms have an appearance of being solid and the effect of being solid when they're not. So this repulsion creates this empty space which allows them to separate from each other and somewhat act like solid balls. But the question you've got to ask is, why does most of the matter in the atom exist in the nucleus, and why is this the most stable form of matter in the universe? So let's consider the nucleus of a typical atom. Now if nature only had what we call the gravitational attraction and the electromagnetic interaction, which are the ones we encounter in our day-to-day lives, a nucleus with many protons would blow itself apart, because the electromagnetic interaction, which between two protons, because they're both positive, will be repulsion, is millions of times stronger than the gravitational interaction attracting and pulling them together. So basically electromagnetism is a much stronger interaction than gravity, so therefore in theory the nucleus should blow itself apart. Now this is still true even though the neutrons don't contribute to the electromagnetic force, only the protons do. So there has to be another force that provides an attraction even stronger than the electrical repulsion of the electromagnetic force. So this force is called the strong nuclear force. Now the strong nuclear force has the following properties. It's got about a range of 3 to 4 femtometers. Now femtometer means 10 to the minus 15 meters. Now this range is about the same as the diameter of a small nucleus. Now it's an attractive force from about 3 to 4 femtometers down to about 0.5 femtometers. Its separation smaller than this, it's a repulsive force, so it prevents neutrons and protons from pushing into each other any further. Now finally, the strong force has these properties due to the properties of the strong force boson, its exchange particle, the gluon. Now if we look at this particular graph here, this graph shows the stable and unstable nuclei as a function of protons against the number of neutrons. Now you'll see here that the black dots are the stable nuclei, the red dots represent the nuclei that exist for millions of years before they decay, and the light blue dots represent the nuclei with a lifetime shorter than 1 second. So you can see our stable and nearly stable nuclei form a narrow band in this graph in the middle. Now you'll notice that for small stable nuclei the number of protons equals the number of neutrons, whilst for a large stable nuclei the number of neutrons is much greater than the number of protons. So why is this the case? Well, in the nucleus, the electromagnetic force only acts between charged particles, protons, whilst the strong interaction acts between all nucleons, both protons and neutrons. Now if the electromagnetic and strong forces are very closely balanced, a nucleus will be unstable, so it will make the nucleus susceptible to radioactive or nuclear decay. So when the strong force is much larger than the electromagnetic force, a nucleus will be very stable and will not decay at any point. Whilst if the electromagnetic force was stronger than the strong interaction, well then the nucleus could never possibly form, because it would just be repelled and would blow itself apart. So this reason is why there are some stable nuclei in the universe and some unstable nuclei in the universe and some nuclei configurations that just never form. Now, for small nuclei, we can get a configuration where the strong interaction is much larger than the electromagnetic interaction when the number of neutrons equals the number of protons. Because you'll notice here that all the nucleons contribute to the strong interaction. The strong interaction is larger than the electromagnetic interaction, and only the protons interact via the electromagnetic interaction. So having the same number of protons and neutrons will give a much larger strong interaction than electromagnetic. However, because the strong interaction only acts over a particular range, to produce stability for large nuclei, where the strong interaction is much larger than electromagnetic, well, we've got to increase our number of neutrons, because the strong force doesn't cover the entire nucleus. So for a large nucleus, if the proton number equaled the neutron number, then the electromagnetic force would equal the strong force, and therefore it would be unstable. So what we've got to do is, to produce this stability, we've got to add more neutrons, which will only interact via the strong interaction and not the electromagnetic interaction. So it will then ensure that the strong interaction is much larger than the electromagnetic. Now eventually though, this is only a bit of a short-term fix, because eventually if the diameter of the nucleus is just so much larger than the strong interaction range, there'll not be a large enough strong interaction produced across the nucleus to make it larger than the electromagnetic interaction. So this means that the size of the nucleus can only really be approximately the size of the strong force interaction, which is why the nucleus is so small in the atom. So let's just summarize these ideas. When the strong interaction is much larger than the electromagnetic interaction, you have a stable nucleus. When the strong interaction is approximately the same size as the electromagnetic interaction, the nucleus is unstable, whilst if the electromagnetic interaction was greater than the strong interaction, the nucleus doesn't form. So the strong nuclear force is much weaker than the electromagnetic force at distances significantly greater than the typical nucleus, but we don't encounter the strong interaction in our day-to-day lives. At shorter distances comparable to a nucleus, it becomes much stronger, so its attractive force is able to overcome the electromagnetic interaction between the protons. But the nucleus is not crushed to a point mass at very short distances, because this strong interaction becomes repulsive and keeps the nucleons apart. Now, so it's important to note that the strong interaction changes properties with nucleon separation, which affects the composition of the nucleus. So like we said before, the nucleus of an atom of size about 10 to the minus 15 meters doesn't really occur, as beyond that the attractive strong force interaction is much weaker than the repulsive electromagnetic interaction, so proton-proton repulsion cannot be overcome. In addition, the nucleus is not a point mass, as at extremely small distances the strong interaction switches from an attractive interaction to a repulsive interaction, so the protons and neutrons remain separate. So we can see the properties of the strong interaction with our particular graph here. So at distances larger than 4 times 10 to the minus 15 meters, the strong interaction does not exist, which is why nuclei can't be much larger than 5 times 10 to the minus 15 meters, because there's not enough strong interaction to overcome the electromagnetic interaction, which is repulsive. Now between 1 and 4 femtometers, or 10 to the minus 15 meters, the strong interaction is strongly attractive. This makes the nucleons stick together and stable nuclei form with diameters of this size, and smaller than 0.5 femtometers, the strong interaction becomes repulsive to ensure the nucleons don't crush to point masses and exist as neutrons and protons. So it's very important at how this works. So to summarize this, at distances less than about 1 femtometers, the nucleus can't form because the strong interaction is repulsive, so it stops the nucleus being crushed. At distances greater than 3 femtometers, nuclei can't form because the strong interaction is 0, so it stops the nucleus being too large, whilst in between here the nucleus can form because the strong interaction is greater than the electromagnetic interaction, so we've got our attractive strong interaction holding our nucleus together. So let's now have a look at particles, antiparticles and photons. So Albert Einstein stated that light was emitted in discrete packets or particles called photons, and you can work out the energy of one photon with our equation of the E is equal to Planck's constant times by the frequency in Hertz. Now Planck's constant is 6.63 times 10 to the minus 34 joule seconds. Now this is one of the most fundamental equations in quantum mechanics. So Planck's constant is one of the most important values in physics. It's proportionality constant between the energy of one photon and its frequency. Now, because it's a small value, this indicates why quantum mechanical properties are only evident on the subatomic scale. Now, this equation indicates to us that electromagnetic radiation is not continuous, but rather comes in discrete packets or chunks. So this equation indicates to us that electromagnetic radiation is not a wave, rather it is a particle. It also shows us that as the frequency of a photon increases, the energy of the photon also increases. Now, as we said before, due to Planck's constant being an extremely small number, photon energy in joules will be a very small value. So as a result, particle physicists use another unit for energy, the electron volt. Now, 1 eV is equal to 1.6 times 10 to the minus 19 joules. Now, you could be given a value of photon energy in electron volts and asked to work out the frequency. So to do this, you've got to convert it back into the SI derived unit, which is the joule, okay, and then you work out your value. Now, you can work this the link out, because we know frequency is equal to wave speed over wavelength. So therefore, the photon energy is equal to Planck's constant times by wave speed over wavelength, which you can write as E is equal to hc over lambda, where c is the speed of the electromagnetic wave. Now, this equation is probably the more common form of the equation because it's easier to measure wave speed compared to frequency. Now, this equation does indicate to us that as the wavelength of a photon increases, the energy of a photon decreases. So this theory states to us that the different parts of the electromagnetic spectrum are actually all different types of photons. So the larger the frequency of the photon, the more energy stored in the photon, the more energetic the region of the electromagnetic spectrum. So we can say that the smaller the wavelength, the more energy stored in the photon, the more energetic region of our spectrum, as you can see here. So the different parts of the electromagnetic spectrum contain the same photons, just with different frequencies. So gamma ray photons contain more energy per photon compared to radio wave photons. And you can see here an example of how to work out photon energy. So you say E equals hf. H is a constant. We know the value of F from the equation. We can work out our value in joules. Same idea if you've been given the wavelength of the photon. So 590 nanometers. We use our equation E equals hc over lambda. H and c are constants. We've got lambda in the question. We can work out the energy in joules. And finally, we can also convert the value from EV into joules by working out our value in EV and then multiplying by 1.6 times 10 to the minus 19 to get our value out in joules. Now, a laser beam is an intense beam of light, but we can also consider laser beams in terms of photons. So a laser beam consists of photons of the same energy. So laser beams are very large streams of photons being emitted, and we say that the photons in the laser beams are coherent with each other. So our laser beam is a very intense, coherent source of electromagnetic radiation. But coherent means that the particles are all in the same phase and have the same frequency. Now, a laser beam therefore has photons which have the same frequency, so therefore they'll have the same amount of energy in each photon. So if we consider the laser beam as a stream of photons, each with an energy of E equals hf, we can assume all of our photons in the laser beam are identical because we've got coherency. So therefore we can work out the values of the entire laser beam. So we can also consider the laser beam as a wave, where all of the wave is in phase with each other. So we can say that when the wave's in phase, they're constructively interfering, so therefore we have a high energy. So there's a phase difference in our wave of 0 pi radians, or we could say 2 pi radians, so no wavelengths or one complete wavelength. Now, we know that the power of a laser beam is the energy transferred per second by the photons. So we can say that the power of a beam is n times by hf, where n is the number of photons in the beam passing a point in each second. So we can only do this because we're assuming that all of the photons in the laser beam are identical to each other. Now, this value of n incorporates the concept of time into the power equation. Now, antiparticles are like mirror images of particles. A particle can be described in terms of its charge, its mass, its baryon number, its lepton number, and its strangeness. Now, antiparticles have the same rest mass but completely opposite all other properties. Now, the notation for a particle and its antiparticle are using the hat symbol. So if the particle is x, the antiparticle is x hat. Now, the first antiparticles were scientifically observed in the 1920s. Now, most antiparticles go by the name of anti energy before the actual particle, such as the antiproton. The only exception to this is the antiparticle of the electron, which is called the positron. So as we can see here, that particles and antiparticles have the same rest mass but have completely opposite values in all other properties. So whilst they have the same rest mass and same rest energy, every other particle property is reversed for an antiparticle. So this includes charge, baryon number, lepton number and strangeness. Now Einstein had shown that the mass of a particle increases the faster it travels. So E equals mc squared relates the energy supplied to the particle to its increase in mass. So when the particle isn't moving, it has a rest mass, which is the minimum mass possible. But when the particle is moving, it has a larger mass, which we call the relativistic mass, which is the rest mass plus an extra amount of mass. So this indicates to us a fundamental link between the energy store of an object and its mass. Now, Einstein indicated that the rest mass of a particle corresponds to the rest energy of the particle. So the rest energy must be conserved in the conservation of energy, and this effect is very noticeable on the scale of particles. Now, as Einstein postulated that the mass of a particle when it's stationary, its rest mass, corresponds to its rest energy locked up in mass, we can say that the rest energy mass must always be conserved in all decays. Now, Paul Dirac predicted that the existence of antimatter, which could unlock rest energy, so whenever a particle and a corresponding antiparticle met, they would annihilate and release this energy into the universe. So it's been realised that on the quantum scale, the scale smaller than subatomic particles, there's a constant flow between annihilation and pair production. So at the quantum level, matter and energy are interchanged between each other, because as humans we're oblivious to this process as it happens on a scale much smaller than our senses can detect. So the constant cycling between the forms of energy and matter on a quantum scale can also be known as the quantum foam. Now the processes of annihilation and pair production have profound consequences on the composition of the universe. So antimatter and matter can carry out two processes. The first process is annihilation. So when a particle meets its antiparticle, the two are attracted to each other due to having opposite charges. So they'll proceed to annihilate. So they'll turn all their matter into energy. So this is observed as two photons. Now there are two photons since the momentum has to be conserved. Beforehand the momentum is zero. Afterwards the momentum has to be zero, which happens because the two particles are moving in opposite directions. So a zero momentum can't be achieved with only one photon, you need two. Now the total energy afterwards must be 2hf, because each photon has an energy of hf, so we can therefore say that the energy of each particle is E0. Now we can actually observe this event, by the way, in a positron emission tachometry hospital scanner, a PET scanner. So a positron emitting isotope is administered to the patient, so this isotope releases positrons. The positrons travel a few millimeters and then annihilate. The two gamma photons are emitted and detected by the scanners, and this allows the scanner to build up an interior image of the body. So what we can say is that the energy before is 2E0, the energy afterwards is 2hf, so therefore 2E equals 2hf, so therefore E0, the minimum energy of each photon, is equal to hf. So this is true because two photons are produced. Now the opposite of annihilation is pair production. That's when matter is created from energy, so it creates a pair of particles, the conventional particle and its antimatter particle. So the photon itself must have enough energy to form the rest mass of both particles. So they must contain enough energy to form the equivalent rest mass of both the particle and the antiparticle. Now because the photon has an energy of hf and the particle and antiparticle have an energy each of E0, we can therefore say hf equals 2E0, so therefore we can say that hf equals 2E0. Now any extra energy above this is found as the kinetic energy in the particles. So this is an important idea, because if the photon doesn't have enough energy to produce the rest energies of the particle and antiparticle, the process simply doesn't take place. That's why it's extremely rare for very massive particles to be produced in this process. So let's take the electron for example. It's got a rest energy energy of 0.511 MeV. Therefore, for pair production, an electron and positron must form from the photon. So therefore, the minimum energy the photon must have is twice the energy of the part of the electron, which is 1.022 MeV, which is 1.64 times 10 to the minus 13 joules. So a photon with less energy couldn't create a positron and an electron. Now, as it's important to note that the photon will always need a little bit more energy than the minimum, because this gives the particle and antiparticle enough kinetic energy to overcome their attraction to each other and just annihilate themselves as well. So that's very, very important. That's actually slightly bigger than the minimum energy required. So it's important to note that if the particles just have their rest mass, the particle-antiparticle will annihilate, but if you wish them to have a little bit more, they'll have enough kinetic energy to get away from each other. So the difference in pair production and annihilation has the following effect. The annihilation of a particle-antiparticle can lead to pair production. Then each photon then produces its own particle-antiparticle. So each photon will then have its own set of particle-antiparticles. So this means that the resultant particles and antiparticles have a smaller mass than the previous particles, as the starting energy is now spread between two photons. Again, these particles, antiparticles, will carry out annihilation. However, the photons produced will have half the energy of the previous photons produced in the last step. So this means that with repeated annihilation, pair production, the energy becomes spread out over the universe, and the possible particles produced are less massive. So this is the reason why energy gets dissipated throughout the universe, and the most common particles in the universe are the ones with the least mass, which is the concept of entropy. Now we can compare and contrast the processes with the following table. In annihilation, you start with a particle-antiparticle, you finish with two photons, so the minimum energy calculation is E0 equals HF. Whilst in pair production, you start with one photon and finish with a particle-antiparticle, so the minimum energy calculation is 2E0 equals HF. Let's now have a look at particle interactions. So there are four fundamental interactions in nature. You've got gravity, which is the weakest interaction in the universe. Then you've got the weak nuclear interaction. You've then got the electromagnetic interaction. And then you've got the strong nuclear interaction, which only works on hadrons. So we can sum up the properties of the different interactions with the following table. Now it's important to note that the strength is how strong the interactions are compared to each other, and the range is how far reaching the interaction is. Now you've got to be able to remember that the different properties of the different types of interactions for your exams. Now it's important to note that an interaction is produced by an exchange of bosons between objects in the universe. So this is a fundamental interaction which produces the macroscopic idea of a force. So here the exchange particles are moving between the magnets, and this produces the electromagnetic interaction between the forces between the magnets that we observe on the everyday level. Now the particles that work here as exchange particles are referred to as virtual particles, since they can only exist for a short amount of time, because the energy needed to produce them is borrowed from the universe. Now Heisenberg's uncertainty principle states that pretty much that the bigger the energy needs to be borrowed, the shorter the time it can exist for. So what this means is the larger the exchange particle, the more energy is needed to be borrowed from the universe, the shorter the time it can exist, so the shorter its range and therefore the size of the field. So if the exchange particle is massless, it requires no energy to be borrowed, so therefore it can exist forever, so its range and the field it produces are infinite. Whilst, like we said before, the larger the mass of the exchange particle, the shorter the time it can exist, the shorter the range of the force it produces. Now, these particles are also referred to as virtual particles because they can only exist for a short amount of time. And in addition to that, if the particle was observed by an experimenter, it would no longer produce a force and would cease to exist, so we can never observe these exchange particles directly. We can only ever observe the effects of the exchange particles. So it was discovered that forces occur in the universe due to the exchange of bosons, or virtual particles, which can also be called exchange particles. So these particles are virtual, as they can't be detected directly, and if we intercepted them we would stop the force acting, so the property of the virtual particle determines the properties of the force. So objects in our universe exert forces on other bodies as they exchange virtual particles, or bosons. So the properties of the exchange particles lead to the properties of the force itself. Now, the exchange particles cannot be observed directly, and the exchange particles transfer energy and momentum between the objects. So virtual particles work a bit like two people on roller skates throwing things to each other. So if person A throws a bowling ball to person B, A slides back when they release it and B moves back when they catch it. So repeatedly throwing the ball backwards and forwards between A and B causes repulsion between the two. So this is the act of exchanging an exchange particle between a repulsive force or interaction. And again, remember that energy and momentum are being exchanged between the two bodies. As you can see here, that is acting to produce a repulsive force. Now imagine the two people on ice skates representing the two bodies, okay, are exchanging a boomerang. So when person A throws it, it pushes them towards B, and when person B catches it, it moves them towards A. So this is like the exchange particle causing an attraction. So the act of exchanging the particle here has caused an attractive force. So again here, energy and momentum are being exchanged between the objects. So just to clarify, in the standard model of particle physics, there are a number of different types of exchange particles. You've got photons, which carry the electromagnetic interaction, W and Z bosons, which carry the weak nuclear interaction, and gluons or pions, which carry the strong nuclear interaction. Now, we haven't yet discovered the exchange particle for the graviton, for gravity, due to its weak nature. However, we do believe it could exist, and it could be called the graviton. So let's just have a look at our different properties. So we've got the graviton, which is the exchange particle for gravitation. This is an exchange particle that's never been observed. You've got the photon, which is the exchange particle for electromagnetism. This particle has no mass, so has an infinite range. So this means that the electromagnetic force has an infinite range. You've got the gluon, which is the exchange particle for the strong interaction. This is a massive particle, so it can only exist for a short amount of time, so therefore the short interaction has a short range. So that, as we mentioned before, it limits how much the strong interaction can act on things. And you've got the W and Z bosons, which are the exchange particles for the weak interaction. Now there are three bosons for the weak force for a really complicated reason. It's to allow the quantum isospin and hypercharge to be conserved in decays. Now the W boson is the largest exchange particle, so has the shortest range, as it exists for the shortest time. So this means the weak force has a very, very short range. Now when exchange particles are exchanged between particles, it can cause the particles to change type. So Richard Feynman soon realised that the general public didn't understand how this works, so he produced diagrams to make this more understandable, which he called the Feynman diagram. So these are diagrams used to describe and show particle interactions and decays caused by exchange particles. So like we said before, the exchange of an exchange particle can lead to a particle change in type. Now it should be noted that the axes aren't really shown on Feynman diagrams, but they can show time and distance, and it is actually more conventional to depict antiparticles as normal particles with the arrow of time reversed. So a Feynman diagram can show how two particles interact and change over time in the universe. Now please understand, it's not a graph, it's a diagram to help people understand what's going on in the particle level. So in our previous understanding, we would have said that a force was causing a particle decay, like beta decay. Now here what we can do is we can look at the actual interaction taking place in certain situations. So for example, we've got the past, which is the particles before the interactions take place. Now we tend to show particles as straight lines on diagrams. We've got the present, which is when the exchange particle is exchanged, causing the interaction. Now we show exchange particles as wiggly lines on the diagram. And we've got the future, which is the particles produced by the interaction. Now we've got some rules for Feynman diagrams. Time goes vertically up on the diagram and space goes horizontally along the diagram. Particles are shown by normal arrowheads and antiparticles by reversed arrowheads. If the particle is stationary, you draw a vertical line. If the particles are moving, you draw a slanted line. When a decay occurs and a boson causes an interaction, a wavy line is drawn between the particle and is labelled with the exchange particle, and the particles produced afterwards are then drawn as a label line. The baryons stay on one side of the diagram and the leptons on the other side, and the W bosons carry charge from one side of the diagram to the other side, and you've got to make sure the charge is balanced. So here's an example of a Feynman diagram. Baryons are drawn on the left hand side and leptons are drawn on the right hand side. Now here the boson is transferring negative charge across the other side, so therefore all of our charges balance. Now one aspect students struggle with the Feynman diagrams is working out which exchange particle to use. So to work out which exchange particle or boson to use in each interaction, look at the following rules. If the interaction is that it causes attraction or repulsion between particles, the interaction is electromagnetism and the exchange particle is the photon. If the interaction is between hadrons and there's no leptons produced, the force is due to the strong interaction and the exchange particle is a gluon or a pion. And if the interaction includes leptons and the particle changes type, their interaction is the weak, so therefore the exchange particle is the W plus or the W minus or the Z. Now let's see if we can work out which W to use in the weak interaction. So if you start off with a positive and it becomes neutral, you can think of the particle thrown away its positive charge, so the boson will be positive. If the particle starts off as negative and then becomes neutral due to the interaction, you can think of it as throwing away its negative charge, so the boson will be negative, so it'll be the W minus. And if it's neutral and becomes positive, it's like it's losing a negative, so the boson is a negative, so it's W minus. If you start off with a neutral particle and it becomes negative, you can think of the particle as losing its positive charge, so the boson, the W, is a positive one. So let's have a look at an example of a Feynman diagram. Remember that these diagrams are showing how the particles change over time due to interactions by exchanging an exchange particle. So here you've got two baryons, so therefore it's the strong interactions. The exchange particle is the pion because there's no particles changing type and there's no leptons present. Here it's due to electromagnetic repulsion, so our exchange particle is the photon. Here a neutron is decaying due to the weak interaction, so it's changing, and there's also leptons present, electrons and anti-electron neutrinos, and also it must be the W plus because it's gaining a positive charge because it starts as neutral and becomes a positive, so therefore it's the W minus because it's gaining a positive charge, so it's throwing away its negativity. Here the proton decays to the neutron, so a positron and an electron neutrino are produced, so you've got a decay and you've got leptons produced, so therefore it's a weak interaction, and as it's starting off as a positive and it's becoming a neutral particle, the proton to the neutron, it's losing its positivity, so it's throwing away its positive charge, so it must be the W plus boson. Now it's important to note that most processes that have nuclear decay occur via the weak interaction. Now what's happening here in this nuclear decay is the W boson has passed from an unstable nuclei into its stable products. So this decay process lessens the impact of the electromagnetic interaction and increases the strong interaction. Now the only exception to this is alpha decay, which doesn't involve leptons or particles changing type, so it must be a decay via the strong interaction. So because it's the strong interaction, the alpha decay is a lot faster. Now in the previous example we just considered a radioactive or unstable nucleus to be an unhappy face. In reality it's more appropriate to say that it's like a bubbling volcano. It's constantly churning and turning, waiting to erupt and emit a form of radiation. But what causes instability and what interactions are found in the nucleus? So there are two interactions which affect the stability of the nucleus. The strong interaction, which is attraction between all the nucleons, and the electromagnetic interaction, which causes repulsion between the neutrons. So like we said before, a stable nucleus is where the strong interaction is much larger than electromagnetic, whilst nuclear stability is where the strong interaction and the electromagnetic interaction are of similar size. So a radioactive nucleus will move towards the stable or ground state by radioactively decaying and producing energy or particles, and this energy will be distributed over a larger number of quantum states. So it can happen by either alpha, beta or gamma decay. In reality there are two types of beta decay, and there's also a fourth decay process that can occur called internal conversion. So alpha decay is when two protons and two neutrons are lost from a nucleus. So the atomic number goes down by 2 and the atomic mass number decreases by 4. So the new element is formed 2 places lower in the periodic table than the original element. So alpha emission is when an alpha particle or helium nucleus is ejected from the parent nucleus. Now you've got a new element formed because we've lost 2 protons. Now whilst this is the same as a helium nucleus, the term alpha is used if this alpha particle has originated from the nucleus. So this is an example of transmutation as a new element is formed, which is formed 2 places lower on the periodic table than the parent element. Now each alpha particle is released with the same kinetic energy as there are no other products produced in the decay, as you can see in this particular animation. Now in beta minus decay, a neutron changes into a proton plus an electron. The proton stays in the nucleus and the electron leaves the atom as a high energy beta particle. So the atomic mass number stays the same, yet the atomic number increases by 1. So we can see here that the process can produce a new element one place higher in the periodic table. So you can see that you lose 1 neutron and gain 1 proton in beta minus emission. Now beta minus emitters are found naturally in the universe but can also be manufactured by bombarding stable isotopes with neutrons. Now the new element produced in beta minus decay is found because of we've gained 1 proton. Now whilst this beta minus particle is the same as an electron, we use the term beta when the electron originates from the nucleus. Now beta minus emission is an example of transmutation as a new element is formed, and this element is found one place higher in the periodic table compared to the parent nucleus. So that's a very important idea, and you can show it here in this particular demonstration. Now, beta plus emission is when a proton is transformed into a neutron and a positron. It's the opposite decay process to the beta minus emission. So in beta plus, you lose 1 proton and gain 1 neutron. Again, we've got a new element because there are a different number of protons. And again, while this beta plus is going to be the same as a positron, the term beta plus is used if the particle has originated from the nucleus. It's an example of transmutation because you've lost 1 proton. As you've got a different number of protons, and this new element is found one place lower on the periodic table compared to the parent nucleus. Now, beta plus emitters aren't normally found in the universe, but they're manufactured if you bombard stable isotopes with protons. Now, gamma decay is there's no change in the makeup of the neutron, it just loses energy in the form of photons. So alpha emission is often followed by gamma ray emission. So the daughter nuclei can be left in an excited state after alpha emissions taking place, and at some point they'll fall to their ground state emitting a gamma photon. So there's no nucleon change, just a change of energy. So it's not an example of transmutation as no new element is formed. Now, a nucleus which has excess energy before gamma decay is in what we call a metastable state. So here we've got a demonstration of gamma ray emission. Now, gamma ray emission can really only occur after alpha emission. Now, when you have looking at alpha and beta decay in a bit more detail, you'll notice that there's an issue with the amount of energy produced in the decay process. Because with alpha decay, each alpha particle is produced with the same rest energy and the same kinetic energy. So all alpha particles travel at the same speed. They obey the conservation of energy mass. And with gamma decay, your gamma photons are produced with a known amount of kinetic energy, so we're conserving energy and mass. But with beta decay, some beta particles had more kinetic energy than others, so there was a variation of energies that the beta particles possessed, which seemed to violate the conservation of energy mass. So what was happening? Well, a physicist called Wolfgang Pauli suggests that the lost energy was carried away by a new particle, so that the total energy of any beta decay is constant. Now, this particle must be chargeless and have virtually no rest mass. So this was the idea of the neutrino. Now, the rest mass of a neutrino is much smaller than the rest mass of an electron. So Pauli realized that the total energy before decay equaled the total energy after the decay if you consider the energy of the neutrino, which was also produced. Because if we didn't consider the neutrino, that the total energies don't equal each other, so therefore we have the beta decay problem. So the neutrino energy comes from some of the kinetic energy of the beta. So what this means is the larger the neutrino, the slower the beta particle, because the neutrino is taking some of the energy away from the beta particle. So this allowed for the conservation of energy. But Pauli also realized that the neutrino produced for a lepton is actually an anti-neutrino to conserve something called the lepton number. Now, our neutrino is pretty much another type of lepton, and there are many different neutrinos associated with the 3 different types. So you've got an electron and an electron neutrino, a muon and a muon neutrino, and a tau neutrino. Now, as a neutrino has always been observed when a lepton is produced. So physicists have said that the lepton is like the dog, and the neutrino is like the flea. So whenever there's a dog, there's always a flea. Whenever there's a lepton, there's always a neutrino. neutrino. So when we now look at beta minus emission, you also produce an antineutrino with your electron, which means that the electron is produced with a variety of kinetic energies. Now the neutrino produced must be an antineutrino to conserve what we call lepton numbers. And in beta plus emission, the beta particles are emitted with a variety of kinetic energies because a neutrino was also produced. Now the neutrino produced must be a standard neutrino due to the conservation of the lepton number. Now, in addition to the traditional decays of the nucleus, there's a fourth nuclear decay, internal conversion. Internal conversion is a process in which a nucleus in an excited state can release its excess energy. So in internal conversion, all of the excess energy is transferred from the nucleus to an orbital electron through the electromagnetic force, and the orbital electron is then emitted and ejected from the atom. Now, both internal conversion and beta decay eject electrons from the nucleus, but there are differences. Beta decays occurs via the weak interaction and internal conversion via the electromagnetic. Beta decays can also produce neutrinos and antineutrinos. Beta decays produce a nucleus of a new element, internal conversion does not. And in beta decay, the electrons are emitted with a range of energies, and internal conversion, all the electrons have the same energy. And finally, in beta decays, the electron is emitted from the nucleus, and in internal conversion, the electron is emitted from the shell. Let's now have a look at the classification of particles. Now, in GCSE physics, you understood that there were protons, electrons and neutrons. However, in 1932, that James Chadwick, when he discovered the neutron, that completed our particle zoo from GCSE physics. Now, unfortunately, from our previous work, we realised that particles can be differentiated via their rest mass, charge, and specific charge. But in 1936, Carl Anderson experimentally found the antimatter postulated by Paul Dirac. So this led to the idea of antiparticles, and the number of particles in our particle zoo seemed to double. Now, like we said, particles and antiparticles have the same rest mass and rest energy, but opposite properties for everything else. Now, if they were the only subatomic particles to exist, our particle zoo would be very small. Now, what happened in 1963 is that when we looked through cosmic rays, we realised that there were lots and lots of different particles, which we called exotic particles. Now, these exotic particles have a much higher mass than the proton, neutron and electron, so therefore they have a high rest energy and will produce in high energy events. Now, over time, these exotic particles decay into smaller ones. Now, the total overall energy and mass does not change. It means that the massive exotic particles turn to many smaller, less massive particles. So we've now realised that the particles we knew about as the common particles on Earth were the smallest stable possible particles to be made, and in fact in our universe there are many more under high energy events such as supernova. You can get many larger particles possible than the smaller stable less massive particles found on Earth. So at the Large Hadron Collider we simulate these high energy events and produce these larger particles to observe them. So in reality there are many different particles and antiparticles possible in the universe. So like a zoo of animals, there are a zoo of particles. So we need to order the particles into different groups or families according to their properties. And we did this by placing particles into different families from their lepton and baryon numbers. So here's an overview of what we call the particle zoo. Now there are two main areas or two main categories of the particle zoo. The fundamental particles, which can't be broken down any further, and hadrons, which are not fundamental particles and are made of quarks. They can be unstable and can decay into other particles. Now all fundamental particles can't be broken down any further. Now all non-fundamental matter has a structure inside of it, so all non-fundamental particles are unstable apart from a few select examples. The proton is a stable hadron. The pion is a stable hadron. Now we can further subdivide this idea of fundamental and non-fundamental matter into different groups. So for our fundamental matter we've got leptons and we've got exchange particles. For hadrons we've got mesons, which are 2 quarks, 1 quark, 1 antiquark, and baryons, 3 quarks. Now your fundamental particles are stable and don't wish to decay, and your hadrons are not stable and can decay further. Now the only baryon that doesn't decay is the proton, as it's the most stable because it has the lowest baryonic mass. Now only hadrons will be subject to the strong interaction, and the fundamental particles are organised according to their properties, and the non-fundamental particles are organised to their properties, which is caused by their quark structure. So leptons, there are three types of leptons, electron, tau and muon, and each accompanying lepton particle has a neutrino which has no charge. Each lepton has a lepton number of +1 or -1. Now fundamentally the only difference between leptons are their rest energies. Electrons are the most common leptons as they have the smallest rest energy, and taus are the least common electrons as they have the largest rest energy. So a muon is a particle that decays into an electron, a tau is a particle that decays into electrons, and they both do this by shedding excess mass as energy. Now hadrons come in two types, baryons and mesons. They're both made from quarks, a baryon 3 quarks, a meson 1 quark 1 antiquark. So an antimeson is just a meson. Now they're much larger than leptons, they're unstable, but all baryons will eventually decay into protons, and only baryons can have a non-zero baryon number. So mesons equals 0, baryon 1, antibaryon -1. Now baryons and mesons can decay as they're made from quarks. When hadrons decay, the quarks change type. Hadrons that wish to decay can decay into smaller hadrons. Now the protons can't decay as they're the smallest hadron, as they're made from the smallest, most stable configuration of quarks. As a meson is a quark-antiquark pair, antimesons do not exist. The antimeson would just be like swapping the quark and antiquark around, so the meson is its own antimeson. Now a meson, which has a non-zero strangeness, is called a kaon. Now kaons are always produced in pairs, and kaons can decay into pions. Now, exchange particles or bosons carry all the forces of the universe. The range of the force depends upon the range of the boson. The mechanism of the force directly relates to the properties of the boson. Now, bosons have a 0 lepton number and a 0 baryon number. Now, we can summarise the particle zoo properties with our following table. Now, as expected, you should be able to recognise the particle the family belongs to from its baryon number and its lepton number. Now, you can tell the difference between mesons and bosons as you've got to memorise the different bosons. Now, let's have a consideration of quarks and antiquarks. To provide an underlying principle to the particle zoo, Murray-Gell-Mann proposed the quark theory, that all hadrons are made from smaller particles called quarks, baryons 3 quarks, antibaryons 3 antiquarks, mesons 1 quark 1 antiquark, and quarks cannot exist in isolation, so we currently believe quarks to be fundamental. So Gell-Mann proposed that baryons are made from 3 quarks. Each quark possesses a fractional baryon number, charge and lepton number. These then add to form the overall baryon number, charge and lepton number of a baryon. Now a baryon can only have an integer baryon number, charge and lepton. There's only certain combinations of quarks that can combine to make a baryon. Now it's important to note the same for antibaryons, and the force holding the quarks together is the strong interaction, so gluons are constantly being exchanged between the quarks to produce this. Now Gell-Mann originally named the quark after the sound made by ducks. Now Gell-Mann was inspired by the quark in James Joyce's book The Finnegan's Wake because he believed there were 3 quarks. Now Gell-Mann proposed that mesons are made of 1 quark, 1 antiquark, and that he also proposed that again they were being held together by the strong interaction. Now it's important to note that quarks cannot exist by themselves. They exist in either 2s or 3s because quarks tend to the most stable configurations. They exist in either pairs or triples. So that's a very important idea, that quarks cannot exist as single quarks, which is called quark confinement. Now there are actually 6 quarks in the universe. Now each type is called a quark flavour. You've got the up quark, the down quark, the strange quark. Now the strange quark gives a particle its strangeness, the charmed quark, and the top quark. Now this is the largest quark and therefore the most unstable, so it's actually the rarest quark in the universe, and it was only actually first observed in 1995. And finally we've got the bottom quark as well. Now Gell-Mann proposed that these quarks along with the leptons and bosons produce everything in the universe, which is what he called the standard model. So our quarks come in 3 different pairs which have contrasting properties, which he called generations. So you've got up and down, the first generation, strange and charmed, the second generation, and top and bottom, the third generation. Now the higher the generation, the more the mass of the quark. This means it's less likely for the quark to exist. This means that first generation quarks are more common than those of third generation quarks, which is why protons and neutrons are made from first generation quarks. So that's a very, very important idea. So this is our standard model of matter. So we've got our 6 quarks up and down, strange and charmed, top and bottom here. So our quarks, the 6 different quarks that combine to form mesons and baryons. Now only quarks experience a strong interaction, and any particle made from a quark quark is referred to as a hadron, and quarks can never exist in isolation. Now only baryons have a non-zero baryon number, and there's also antiquarks found in the antimatter standard model. Now again, antimatter has the same rest mass as matter but the opposite other properties. You've then got leptons, which are electrons, muons, taus and neutrinos. Leptons do not experience a strong interaction, and they only experience the weak and the electromagnetic interaction if they are charged. They can have a non-zero lepton number, and we've got antileptons found in the antimatter standard model. Now again, antimatter has the same rest mass but opposite other properties of the particle components. You've got your exchange particles, which mediate a force, energy and momentum in the universe, and the properties of the exchange particle lead to the properties of the force interaction. Now these particles are referred to as virtual particles since they only exist for brief amounts of time and can never be observed directly. Now we observe quarks by firing our electrons at neutrons and protons and realizing they were scattered at large angles, which indicates that neutrons and protons were not of uniform density but had a point-like charge inside of them, the quarks, which is very similar in experimentation to Rutherford scattering, except it was carried on a much smaller size. So it showed that this scattering meant that there was an internal structure to the protons and neutrons. So we've got our baryons of 3 quarks, our antibaryons of 3 antiquarks, and our mesons are 1 quark, 1 antiquark. So our baryon is a proton, which is up, up, down. Another baryon is a neutron, which is down, up, down. The antibaryons could be 3 antiquarks, and a meson could be 1 quark, 1 antiquark. And you can work out the particle family from the quark composition. So here's our proton. Here's our neutron. Now when you change your baryons, like from a proton to a neutron, what is happening is 1 quark is changing flavour, and the force responsible for this is the weak interaction. So we're changing our quark's character. So only the weak interaction can change a quark's character. So we observe change in a quark's character as a particle change in type. So the exchange of a W and Z boson causes a quark to change character. So that's very, very important, as shown here in the opposite way around. Now again, you can work out your antiparticles from the opposite structure of your normal particle, and you can deduce the structure of a meson from its properties. So you must work out the charge of a meson to work out what possible quark antiquark could sum together to that charge. If the meson contains either a strange or an anti-strange quark, it's a kaon, and the only meson which can have strangeness is a kaon. Now other mesons like the pion cannot contain a strange quark, only the other quarks. So you can deduce them from the information given to you in your data book. Now again, please remember the quark properties should all add up to give the overall properties of the particle. So here's an example of us doing that. So the properties of the up and the down add together to give the properties of the proton. Again, is shown here. So finally, let's now have a look at the application of the conservation laws. So it's been observed that exotic heavier particles will over time change into lighter, more stable particles. So this process is called the particle decay, and it's caused by an exchange of an exchange particle. It's similar to nuclear decays, but particles are changing from one type to another. So particle decays occur as they want to exist as low energy, more stable particles. So the heavier particles don't have to decay back into the more stable products that produce them if we produce them from our more stable particles by get them in high energy situations, because there are many different decay pathways based on probabilities. So particle physicists can examine the different particle decays and use this to understand how the fundamental forces work. So for a particle decay to occur in the universe, the following quantities need to be conserved between the particles before and after the decay. You've got the same total energy mass before and after, the total momentum before and after, the total charge before and after, the total baryon number before and after, and the total lepton number before and after. If all of these properties are conserved in the decay, then the decay is observed in the universe. If a property is not conserved, we say the decay does not occur due to a violation of that property. So the decay doesn't occur due to a lepton number violation. Now at A level, you must be aware that energy mass and momentum need to be conserved, but you don't need to calculate them. But you do need to prove that charge, baryon number and lepton number are conserved in a particle decay. So what you will do is, if you're given a decay in an examination, you've got to check if the decay occurs by drawing a property table. So you look at the charge. Now the row has to be the same before and after to conserve charge. The row has to be the same before and after to conserve lepton number. and this row has to be the same before and after to conserve baryon number. So all rows must be conserved for a decay to take place. So you'll see here that you can work out your overall charge, lepton number and baryon number before and afterwards, and see that if they're conserved, that the decay will take place. Now you need to recognise what a family of particle belongs to and deduce its properties based on that, which does take practice. Now you can abbreviate your properties in your table as shown. Now when all values are conserved, a particle decay occurs in the universe. Now, there were several issues with our laws of particle decays. When we analysed the conservation laws with the particle decays that occur in the universe, there were some decays that should happen and could happen, but don't happen, and we never observe them. So there must be another quantity which needs to be conserved in a particle decay. So our laws of physics were incomplete, and in addition, certain particles like kaons were created easily in particle collisions, yet decayed much more slowly than expected for their large masses. So they should be decayed by the strong interaction, but instead were decaying by the weak interaction. So another quantity must be causing this. So our laws of physics were incomplete. So how do we solve this? To explain these problems away, we came up with a new particle property called strangeness. Now strangeness was postulated to be conserved in any interaction with a strong, but doesn't need to be conserved in the weak interaction. It's literally strange. So this explained why certain decays didn't occur, they didn't conserve strangeness, and this explained why certain decays took a long time to occur. They conserve strangeness, so the decay can only occur, they don't conserve strangeness, so can only decay via the weak interaction. Now some physicists do believe strangeness to be a fudge on the particle model due to a lack of fundamental understanding. So what do we say? That particles which have a strangeness property all decay through the weak interaction, they decay into pions, which are referred to as kaons, that they don't decay into pions which have different rest masses which are greater than the proton's rest mass and decay into protons and pions, and they must be created in pairs. Now in our modern understanding, strangeness is conserved during the strong and the electromagnetic interactions, but not during the weak interactions. So this is why this means that the lightest strange particle kaons can't decay by the strong interaction and must decay instead by the much slower weak interaction. Now in most cases these decays change the value of strangeness by about 1. So this is why kaons are easy to produce but are difficult to decay into other particles. They can be produced via the strong interaction but only decay via the weak. However, this doesn't necessarily hold in second order weak reactions where there are mixtures of different K mesons, but all in all the amount of strangeness can change in the weak interaction by +1, 0 or -1. So Gell-Mann solved the kaon problem in physics by inventing a new particle property for all particles, strangeness. So it must be conserved in the strong interaction but can change by +1 or -1 in the weak interaction. Now originally this was a bookkeeping device to help explain patterns. However, over the next few years we discovered that baryons and mesons are made from quarks, and one quark was causing all this strange behaviour, so we called it the strange quark. So the weak force causes quarks to change type, and it can cause a strange quark to turn to a different type of quark, that therefore strangeness is not conserved. However, still to this day we don't really know why the strange quark is strange compared to all the other quarks. We don't have a fundamental understanding of what strangeness is. So just to clarify, strangeness is always conserved in strong interactions. It can change by 0, +1 and -1 in the weak interactions. So the strange number can change by +1 and -1 via the weak interaction only. If the strange number changes by more than +1 and -1, it does not happen. And then finally, if the strangest number is conserved, the decay can happen either via the weak or the strong interaction. Now in previous lessons we've used particle Feynman diagrams, but you can also express these Feynman diagrams with quark structures as well as the particle structure. So looking at the particle decays in terms of quarks and leptons is a fundamental way of considering the situation. Now you only have to bold the quarks which change in the decay process. So in the beta decay process, the down quark can change into an up quark, and on the particle level it appears the neutron turns into a proton. Now, the weak force is exchanged between the quarks underneath the particle level. So a true Feynman diagram should be on the quark level, since this is where the exchange particles operate. Now, you can see here that you can observe your different quarks changing in your Feynman diagram. Now you could be able to state the quark Feynman diagrams for both beta minus and beta plus decay, as you can see in these particular diagrams. Now it's noted that with beta minus decay, again, it only occurs in free neutrons, as it's becoming positively charged, so as it's thrown away it's negative, it's a W minus boson, which is the exchange particle. Whilst with beta plus decay, it occurs in protons in the nucleus, as it's becoming neutrally charged, so it's the W plus boson, which is the exchange particle. Now again, you can show in your conservation diagrams the quarks that are changing character and the leptons in the decay. Now as time goes on, we continue to develop our understanding of particle physics. Now new theories are created to explain observations from experiments. Now physicists can hypothesize new particles and the properties they should have, and experiments then carried out to observe these particles and their properties. Now to carry out investigations in particle physics, physicists need to work in large groups to do this. This is because particle accelerators are expensive and so are difficult to construct without a large amount of funding. It's again because working in large groups allows the various different skills and talents to be pooled together to help explain observations. It's because particle physics experiments produce lots of data which can only be analysed quickly when many physicists work on them, and it's because working in large groups allows work to be checked and peer reviewed very quickly. So let's summarise what we've looked at in this particular revision session. We've looked at the simple model of the atom, the atomic mass unit, the charge and mass of the proton, neutron and electron in SI units, the specific charge of the proton and the electron. We've looked at the idea of the notation of used in nucleons as well. We looked at the strong nuclear force, its role in keeping the nucleus stable, it's a strong range attraction up to about 3 femtometers and a very short range repulsion closer than 0.5 femtometers. We've looked at the photon model of the atom with E equals hf equals hc over lambda. We've looked at that for each type of particle. There's a corresponding antiparticle. We've compared particle and antiparticle masses, charge and rest mass. We show that there's a positron, antiproton, antineutron and antineutrinos as antiparticles. Have knowledge of annihilation and pair production and the energies involved. We know that there are 4 fundamental interactions: gravity, electromagnetic, weak and strong nuclear. That there's the concept of the exchange particles, knowledge of the gluon, the Z and the graviton won't be actually needed for this particular specification. That we know that the electromagnetic force has the virtual photon as the exchange particle, the weak interaction down limited to beta minus and beta plus decay, electron capture and electron proton collisions, W plus and W minus as the exchange particles. And then for unstable nuclei, we know what alpha and beta decay, known equations for alpha decay, beta decay and the need for the neutrino, and that the existence of the neutrino was hypothesized to account for the conservation of energy in beta decay. We know that hadrons are subject to the strong interaction. There are 2 classes of hadrons, baryons and mesons. Understand baryon number, conservation of baryons number. The proton is the only stable baryon. The pion is the exchange particle of the strong nuclear force. Kaons are particles that can decay into pions. We know about leptons as electrons, muons and neutrinos and their antiparticles. We know about lepton numbers as a quantum number and the conservation of the lepton number for muon and electron leptons. That muon acts as a particle that decays into electrons. We know properties of quarks and antiquarks, their charge, their baryon number and their strangeness. Combinations of quarks and antiquarks are required for baryons, antibaryons and mesons, and the decay of the neutrons should be known. And we have applications of the conservation law for charge, baryon number, lepton number, strangeness to particle interactions, and then you should recognise that energy and momentum are also conserved. And finally, we've got strange particles. That strange particles are particles that are produced through the strong interaction and decay through the weak. Strangeness as a quantum number to reflect that strange particles are created in pairs, the conservation of strangeness and strong interactions, and that strangeness can change by 0, +1 or -1 in weak interactions. Hello and welcome to this revision session on quantum physics, which is part of the AQA A-level physics specification. So in today's revision session, we're going to focus on the key concepts of quantum physics and see how they work. Now the first topic we want to look at is the photoelectric effect. Now the photoelectric effect is the emission of electrons from a metal surface when electromagnetic radiation is shined upon it. The electrons are emitted off the surface as they're given enough energy by the electromagnetic radiation radiation to overcome their attraction to the nucleus and become free. So the electromagnetic radiation has given those electrons in the metal energy that's ionized the electrons, and they left the surface of the metal and they form something which is called photoelectricity. Now it's important to note that the minimum amount of energy needed to overcome the electron attraction to the nucleus, which is holding the electrons in the structure, is called the work function. Now, as electrons require different amounts of energy to overcome their attraction to the nucleus as they exist in different orbitals or different parts of the metal, we define the work function as the minimum energy needed to release an electron from the surface. And the work function is unique to every element since they all possess different electrostatic attractions between their nuclei and the electrons. Now, it's important to note that the photoelectric effect is proof that electromagnetic radiation must act like a particle. This is because observations from the photoelectric effect do not follow the theorized behavior of wave theory, because according to wave theory, if the electromagnetic radiation was in the form of a wave as it hit the metal surface, then the intensity of the wave would affect how many electrons are emitted. And in addition, this was not observed in our photoelectric effect, as intensity did not affect how many electrons were emitted in the photoelectric effect. So therefore we concluded electromagnetic radiation could not be a wave in this particular situation. Now, according to wave theory as well, because the energy is being slowly absorbed by the metal surface, there will be a delay between the absorption of the energy from the wave and the emission of the electrons from the metal surface. Now, this is not observed in the photoelectric effect. Electrons are emitted instantaneously after radiation is shined on a metal. This was proof that the electromagnetic radiation was not a wave, rather it was acting like a particle. And we consider these streams of particles to be called photons, each with an energy of hf. Now, it's important to note that an electron in the metal can only absorb one photon at a time. This means the emission of electrons happens instantly, as only one photon is needed to be absorbed by the electron. So it also means the only factor which affects how much energy an electron can receive is the photon energy. Now, because each electron can only absorb one photon at a time, the photon energy is the only factor that affects if an electron is emitted. Now, the only factor in the photon energy is the frequency of the radiation. Now, intensity is not a factor to determine if individual photons have enough energy to make the electrons overcome their attraction to the nucleus. It's important to note it's the frequency of the radiation which determines if there is electrons emitted. The higher the frequency, the more energy each photon has, the more energy received by an electron, therefore it's more likely the energy delivered will be above the work function. So that is the factor that determines if electrons are emitted. So, the only factor which affects photoemission is the frequency of the photon, and the minimum frequency to overcome the work function is called the threshold frequency. Now, it's important to note that any energy above the work function delivered by the photon goes to the kinetic energy of the emitted photoelectron. So this means the frequency of a photon determines if electrons are emitted and the speed of those electrons when they are emitted. The higher the frequency of the photon, the greater the speed of the emitted photoelectron. We can see this in this particular animation. Here the photons have energy above the work function due to having a frequency above the threshold. This causes photoelectricity. Whilst in this particular situation, photons have energy below the work function due to having a frequency below the threshold, and this causes no photoelectricity. So we can consider each electron in a potential well due to their attraction to the nucleus. The potential well is caused by the electrostatic attraction between the nucleus and the electron. The attraction is dependent on the energy orbital the electron is in. It would be a maximum if it was closest to the nucleus in its ground state. It would be the minimum if it was the furthest orbital away from the nucleus. Now, remember, we define our energy needed to overcome the attraction as the work function, which is a minimum energy. Now, it's important to note that we tend to give this value in electron volts because the value in joules is so small, and like we mentioned before, the work function for each element is in fact unique. weak. Now, like we said, an electron can absorb the energy of one photon at a time to escape its potential well. Now, it's indicated that's a key principle of quantum mechanics, of quantum physics. Now, this shows us that electromagnetic radiation comes in chunks of energy, the energy of a photon. So electromagnetic radiation is not continuous, rather it is discrete. This means, like we said before, photon intensity is not a factor when the photon does not have enough energy to overcome the work function. So if the work function is greater than the photon energy, hf, there's no electron emission. If the work function equals hf, well, the electron is emitted from the surface of the metal, but it can't move any further. Now again, the electron has passed the threshold of photoemission, so the frequency which brings enough energy for the photon to have the work function is called the threshold frequency. Now below the threshold frequency, intensity does not affect photoemission. Now above the threshold frequency, the intensity can affect photoemission as each photon has the energy to overcome the work function. Now if the work function is smaller than the energy of the photon, the electron will escape the surface of the metal, and the kinetic energy of the electron will be the energy from the photon once the work function is being subtracted. So we can assume in this situation that no energy is lost to the internal energy of the surroundings on the photon. So our equation for photoelectricity is the photon energy equals work function plus the kinetic energy of the emitted electron. So say for example our photon energy was 30 eV and our work function was 20 eV, then the kinetic energy must be 10 eV. So the energy of the photon splits between the energy of the work function and the kinetic energy of the emitted photoelectron, which you can see in these different situations. Now change in intensity will not overcome the work function, so therefore it's only the frequency that affects your photo emission. The intensity can only become a factor once the photon has more energy than the work function, the frequency is above the threshold, since that work function has already been overcome. Now again, the other proof of the idea of why the photoelectric effect is proof of the particulate nature of light is that A, the intensity is not a factor on photo emission, and secondly, there's no delay between the radiation being shined on the surface and the emission of the electrons. So in this example, the photon energy is less than the minimum required for the electrons to escape, so no electrons are emitted from the surface. The photons have a lower frequency than the threshold. In this situation, the photon energy is greater than the work function, so photoelectrons are produced at a range of kinetic energies up to a maximum value. So the photons have a higher frequency than the threshold. Now we gain a range of kinetic energies as the work function assumes all of the emitted electrons are at the surface of the metal, which is not the case in reality. Now the photon energy is large enough in this instance to cause emission, and if that's the threshold frequency, photoelectrons with zero kinetic energy must be produced. So what do we know about the photoelectric effect? It's the emission of electrons from the surface of a metal due to the absorption of radiation. We know that light must behave as particles called photons in the photoelectric effect, as only the frequency of radiation affects whether electrons are emitted, and there's no delay on the emission of electrons after the radiation is shined on the surface. The frequency affects if electrons are emitted and the speed at which they are emitted. The intensity affects the amount of electrons emitted per second, and the work function is the minimum energy needed for an electron to be emitted due to the attraction between the electron and the positive nucleus. In our assumptions here that one photon is absorbed by one electron, the electrons are found at the surface of the metal and there's no energy dissipated in this transfer. So we can write this out mathematically and say E equals HF equals work function plus a half mv squared. Now remember, the work function is considered a minimum as we assume the electron is at the surface of the metal, so therefore if the work function is a minimum value, that tells us that the kinetic energy of the electron in this equation must be a maximum value. This happens because our photon energy splits between the work function and the kinetic energy. Now in reality you gain a variation of energies, a variety, as the electrons are different distances from the surface of the metal and the actual nuclei themselves. Now a consequence of the photoelectric effect is that electrons are emitted from the surface of a metal. Now the true name for the emitted electrons are photoelectrons, electrons produced by photons of light. Now we can measure their kinetic energy by looking at another property of electrons, which is not their mass or their velocity. What we can do is look at the idea that the electrons are moving in a current off the surface of the metal. Now the kinetic energy of the electrons emitted is manifested as an electrical current. current. Now if we place a negative charge at the opposite end of the metal surface from where they are emitted from, the electrons emitted will be repelled by the negative charge. So what happens is the electrons will slow down and eventually stop moving. So our reading for current will go to 0 as the charge is no longer flowing. So the kinetic energy store of the emitted electrons is transferred into an electrical potential energy store. Work is being done. Now if we again assume that no energy is dissipated in the process, we can equate the two energy stores, and kinetic energy is a half mv squared, electrical potential energy is QV or EV when we're considering electrons. So therefore we can equate the two and say a half mv squared equals EV. So therefore we can rearrange this and say that V in this instance in Vs is the potential difference needed to stop the electrons from moving, the stopping potential. So the kinetic energy is equal to EV, where E is the charge, is 1.6 times 10 to the minus 19 coulombs. Now this assumes the kinetic energy of the photoelectrons is a maximum value, so this is the stopping potential that will stop all electrons. So now we can say our original equation was E equals HF equals work function plus a half mv squared. So now we can sub out that kinetic energy term of a half mv squared and sub in our stopping potential term as they equal each other. Now if we wanted to as well, we could also state that the work function is H times by F0, where F0 is the threshold frequency. Now when analysing the photoelectric effect, we can do this with an experiment and graph various quantities. So what we want to do is measure the kinetic energy of the electrons via the stopping potential concept and alter our photon frequency. So you can do this with the following equipment. We can alter the photon frequency shining lights of different colour onto the surface of a metal. Now the intensity of the light would not affect the results achieved. We can measure the kinetic energy of the electrons with the monitor of the stopping potential on the voltmeter. The stopping potential will be the value of the potential difference which causes the electrons to stop flowing, and this will cause the current in the circuit to be 0. So to find the stopping potential, you alter the PD and record the value of PD, which causes the current on the ammeter to read 0. Now again we can use the stopping potential to then calculate the kinetic energy of the photoelectrons. Now you can then plot the idea of the kinetic energy of the photoelectrons against frequency. Now the greater the photon frequency, the greater the energy inputted into the surface, the greater the emitted kinetic energy of the electrons. So you can see the following graph. Now the graph does not intersect at the origin because of the work function of the metal. We can extrapolate the line back to actually determine our work function of our metal. So if we have kinetic energy as our y-axis, we have frequency on our x-axis. This tells us that the negative of the y-intercept is the work function. It tells us that the x-intercept is the threshold frequency, and it tells us that the gradient of our line produced is Planck's constant. Now this means all metals will produce lines of best fit of the same gradient as each other. So it's important you can use kinetic energy frequency graphs to work out the following properties. The gradient is Planck's constant, the y-intercept is the negative work function, and the x-intercept is the threshold frequency. And we can use this to determine different properties about the photoelectric effect. Now the next topic we're going to look at is energy levels and photon emission. Now Bohr suggested that electrons do not orbit, rather they exist in energy levels or shells or orbitals, which can be imagined a bit like a flight of stairs. We have the nucleus at the bottom and outer the atom at the top. Now each step is an energy level that the electron can exist upon. So we can call that an orbital, energy level or shell. Now the energy levels close to the nucleus have a low energy because there's a high electrostatic attraction binding the electron and the nucleus together. The energy levels far away from the nucleus have a high energy as they have a low electrostatic attraction binding the electron and the nucleus together. We call the energy level nearest the nucleus the ground state. We call the outermost energy level from the nucleus the valence state. Now an electron can exist on an energy level without losing any energy. It has the energy of that level, but electrons cannot ever exist between the energy levels. So whilst the original nuclear model had this idea, in fact we believe that electrons exist in stable energy levels around the nucleus. Now remember our rules of our atom. The electrons can exist on different energy levels but not in between. The ground state is the state closest to the nucleus. The valence state is the outermost state from the nucleus. Electrons can transport to higher levels, but that requires energy, and electrons can transport to lower levels, but that requires energy being transmitted to the surroundings. So in this example, the atom has 3 possible orbitals. So there are 3 possible energies the electron can have to exist within this atom. So it is here, or here, or here. Now the shell at the bottom represents the innermost shell, or the ground state. The shell at the top represents the outermost shell, or the valence state. So if you had an energy level value for your energy level, it will tell you the energy you need to exist at a particular energy level. Now the lower the level, the less energy is needed, because it's easier for the electrons to exist near the nucleus, because there's a greater attraction from that nucleus. Now if you want an electron to move up an energy level, it needs to be given the exact right amount of energy to move to the correct level. So if more or less energy is given, it does not happen. Now this is true if it's a photon exciting an electron. A colliding electron with the atom can provide this energy to cause this to move up, but it can keep its remaining energy after that. Now when an electron is moved up an energy shell by being given energy, we say it is being excited. We've had the process of excitation. So for example, if you have a photon being absorbed with a difference that is not the energy level difference, then nothing would happen. So 23, 27, 32 would not happen. But if you had a photon with enough energy to cause an exact difference, like such as 30 joules, that can cause an electron to move from level 2 to level 3, because that's an exact energy level difference between the levels in the atom. So in this case, it will cause it to jump up. Now to work out if excitation occurs, you work out the energy level difference and see if the photon has that exact energy. This is the reason why the electron needs the exact energy, because it has a wave nature. The electron is switching frequencies, similar to how a standing wave is formed of discrete frequencies on a string. Now the fact that either the photon supplies the energy or does not supply the energy for excitation is further proof of the particulate nature of radiation. So it is proof of the particle nature of light, because one photon can only absorb one electron at a time, similar to the photoelectric effect. Now it's important to note that the electron does not travel between the shells when it jumps, rather it disappears from one shell and reappears on another. There is a quantum leap that takes place. Now it's important to note that if the electron receives more energy than the energy needed to leave the outer shell, the top level, the electron will leave the atom. This is called ionization, and the energy is given by an electron colliding with this atom. Now it could also be any other particle, but it's most likely going to be another electron. Now it's a common misconception to think that the electron is ionized when it reaches the outer shell. No, it needs to leave the outer shell and reach the ionization level. Now unlike excitation, ionization can occur when the energy level difference or higher is given by a photon, and the excess energy goes to the kinetic energy of the electron emitted. Now in ionization, not all of the kinetic energy of a colliding electron needs to be passed on to the atom in a collision. It is very similar to the photoelectric effect. Now the photoelectric effect is similar because it's the ionization of electrons from a metal surface due to the absorption of electromagnetic radiation. Now ionization in general is just the emission of any electron from any atom due to energy being given to it. Now it's important to note that you can consider ionization to be like an extreme form of excitation. Now in reality, whilst we might use joules in some examples, it's a lot easier to express your energy level calculations in a different unit, the electron volt, which is the work done when an electron is accelerated through a potential difference of 1 volt. Now 1 eV is 1.6 times 10 to the minus 19 joules. So if you wanted to convert from eV into joules, you multiply your value in eV by 1.6 times 10 to the minus 19. If you want to convert a value from joules into eV, you divide your value by 1.6 times 10 to the minus 19. Now we've talked about de-excitation, but the process of excitation is moving an electron up the energy levels but not leaving the atom, and this can happen when the energies correlate to the exact differences in energy levels. So in this case, the energy required to excite the electron in level 2 to 3 is 1.9 eV. So again, to work out if excitation occurs, you work out the energy level differences and see if the photon has this energy. Now we can represent excitation energies with the following diagram, and these are the energies of the photons that would cause the electrons to move up an energy level. Like we said before, ground state is the lowest possible state of an atom, and the top level is the amount of energy to ionize the atom, which is written with a dashed line as it represents the boundary of the atom. atom. Now the number on the side represents the amount of energy found in the shell. Now the most common way of writing the structure of the atom though is not with excitation energies, rather with ionization energies. Now what this tells us is, once again, the top level is the energy needed to ionize the atom. The bottom level is the ground state, the most stable state of the atom. Now the number on the side now represents the energy needed to ionize an electron found in this shell. So energy levels or ionization energies are always written as negative values because they're relative to the ionization level. So for example, minus 2 eV means that 2 eV is needed for the electron to be ionized. Now we define zero energy as the energy required for the electron to leave the electrostatic attraction of the nucleus. This is because now there's no electrical potential energy between the electron and the nucleus. Now it's important to note that when we're looking at electrical and gravitational fields, energy is always defined as zero at infinity. So we state an object in this case is at infinity if it's outside of the atom. Now, we've got to always give our energy levels in terms of negatives, as the electrons are bound to the nucleus, so require energy to release them. The electrons are in essence in debt to the nucleus, so work needs to be done to an atom to liberate the electrons. So the negative energy means the atoms need to take energy in, work is done from the surroundings to liberate any electrons. So for example, to liberate any electron in an energy level, you might have to give an electron at least 5 eV from energy level 3. Now it's important to note that an electron is excited when it can leave a shell and move to a higher shell, such as this example, but if it does so, it then leaves a space or vacancy at the shell it departs. So atoms don't like to have vacancies in their inner shells. It disrupts their stability, and in addition the electrons in the higher levels are less stable than the inner shell electrons, as they need more energy to exist in these levels. So sooner or later the vacancy is filled by an electron from an outer shell dropping down, as the electrons prefer to exist at lower energy levels as they are more stable. Now which one does this is dependent on probability. Now this is why electrons fill up with certain shells first. It's more energetically favourable to do so. So when an electron goes down levels, the excess energy of the electron is shed as it moves down, which we call de-excitation or relaxation. Now in de-excitation, the excess energy shed will be as a photon. Now this photon will have an energy equal to the energy level differences of the levels. Now atoms can only release photons of certain energy corresponding to those energy level differences. Now in this case it will be going from -2 to -15, so the energy of this photon is 13 eV. That's the energy the photon released from the atom. Now this explains why certain substances fluoresce or glow with visible light when they absorb radiation. It's why different elements glow with different colours in the chemistry flame tests. Red visible light is longer wavelength light, so the photon produced from a small energy level difference that the electrons are moving between in the atom. Blue visible light is shorter wavelength light, and it's a photon produced from a large energy level difference that the electrons are moving between in the atom. So if the energy level difference in the two levels is small, then the photon produces in the infrared spectrum. If the energy level difference between the two energy levels the electron moves between is very, very large, the photon produces in the ultraviolet spectrum. Now this explains why ultraviolet photons are so rare. You need a large energy level difference in your atom to produce them. So excitation is the process of electrons moving to higher energy levels from lower ones. It's an instantaneous process, and it requires energy to be placed into the atom. Now excitation can occur either due to the absorption of a photon by the atom, or by the transfer of kinetic energy from a colliding particle such as a free electron. Now excitation requires the exact energy level difference between the levels to take place in the atom. Now the photon will require the exact difference between the two levels, otherwise excitation will not take place. A colliding particle such as an electron will only lose the exact energy level difference from its kinetic energy store. Now de-excitation is the process of electrons moving into lower energy levels from higher ones. De-excitation is an instantaneous process. De-excitation releases energy from the atom in the form of a photon. The energy of the photon released is equal to the energy level difference between the two levels the electron moves between. The larger the difference in values, the greater the energy the photon has. The smaller the difference in values between the levels, the lower the energy the photon has. So We can look at this and explain why certain substances fluoresce. Atoms in the substance will absorb energy and become excited. When they de-excite, they emit visible photons. This means when the original source of excitation is removed, the substance will stop glowing. An example of this is going to be a tube such as this, a fluorescent bulb, because what happens is you have an electrical current through your tubing that will cause excitation to the atoms inside the tubing. They will then relax or de-excite, and they will release photons, which we can observe as visible light. So what we're going to look at is this idea of fluorescent lamps now, of electrical current, excitation, relaxation, photon emission. So a fluorescent tube works as the free electrons flowing through the tube due to the current hit the mercury atoms inside the fluorescent tube and excite them. Now this is caused by applying a high voltage across the fluorescent tube. Some of the atoms will also be ionized by the collisions with the free electrons and each other. Now eventually, after excitation has occurred, the mercury atoms de-excite and emit photons of energy as ultraviolet radiation. This happens as the energy level difference between the different levels in mercury equates to UV photons. So what then happens is the photons of UV radiation hit the phosphorus atoms on the surface of the tube and excite them. This happens as certain energy level differences in phosphorus allow for UV photons to be absorbed to cause excitation. Eventually, the phosphorus atoms de-excite and release the energy as visible light photons. This happens as certain energy level differences in phosphorus equate to a visible photon. Now there are certain energy level differences in phosphorus that equate to UV photons being emitted, which is why a lamp is never 100% efficient. So stage 1, ionization and excitation of the mercury atoms occur as they collide with each other and electrons flowing through the tube. Over time, the mercury atoms emit photons when they de-excite in both the UV and visible spectrum. The UV photons are absorbed by atoms of phosphorus coating on the surface of the light, which excites these atoms. They then de-excite and emit visible photons. Now it's interesting to note that when we shine light through a prism, we get a continuous spectrum because there's no break in that spectrum. However, if we place a cold gas between the light source and the prism, some of the lines of the spectra disappear, so we call that an absorption line spectra, because the cold gas was absorbing some of the energy from the visible light source. Now sometimes if we look at the spectra given off by a hot gas placed through a prism, we can see lines of the spectrum appearing, which we call the emission line spectra. Now this occurs as the hot gas is only emitting certain frequencies of energy. So we can have our continuous spectra, our emission spectra and our absorption spectra, which tend to be opposites of each other. So let's try and understand the physics behind this. Line spectra provide evidence for the transition between the discrete energy levels in atoms. So let's consider how they work. So what happens is when de-excitation occurs, the electrons drop their levels, they will release a photon of a certain energy which is equal to the energy level differences, and that can then form a line on your emission spectra. Now the number of possible jumps downwards gives you the number of possible lines in the spectrum. So it's an important idea to note that the number of lines in the spectrum tells you the possible jumps in the energy levels of an atom. Now the emission spectra is unique for elements, as each element have a different energy level number, so a different energy level difference, so it means they will emit photons at different frequencies, and the frequency of the photon absorbed in the absorption spectra is the same principle, just the other way round. So again, you need to be having the exact energy level difference between two levels for your photon to cause excitation of electrons, and so you can work out what the energy of the photons need to be. So this results in a dark line in your absorption spectra, because if the energy of the photon is the exact difference of two levels, that will be taken in by the atom and cause excitation. So our black lines are the actual values of energy, which are exact energy level differences and cause absorption to occur in your atom. So again, it's unique for every element, as each element has different energy level differences. So an emission spectra is caused by de-excitation, by the atom emitting photons, and the absorption spectra is caused by excitation, the atom absorbing photons, but they're both caused by electrons moving between energy levels. The emission one by electrons moving down the spectra and absorption by the electrons moving up the particular levels. So spectra only occur as the atoms carry out excitation and de-excitation. So they are experimental proof of the particle nature of light, in addition to the photoelectric effect and the ultraviolet catastrophe. Now, as the line spectra of each element is unique due to each element having different energy levels, you can identify elements present in the sample, because you'll excite a sample of a substance, let the sample de-excite and record its emission spectra, compare the emission spectra with known samples and find the matching element from the matching sample. Because it doesn't matter where the sample is excited, the line spectra will always be the same. That's how we determine what was inside objects like stars, like the sun. We can determine what is in supernovae, and we can determine if an object is redshifting or it's not by looking at their line spectra. So emission spectra show the wavelengths of different photons emitted by atoms when they de-excite. The absorption spectra show the wavelengths of different photons absorbed by atoms to excite the electrons. So if we look at this example, an electron in the fourth shell could de-excite to the third, to the second, or the first shell. So what happens is when they do this, they release a photon with an energy equivalent to the difference between the two levels they're moving between. You can then use this to work out the wavelength of that particular photon. Now, it's important to note the energy when you do this must be in joules, not EV. So you can do this for every single transition in an atom. So you can find them from 4 to 3, 4 to 2, 4 to 1, so on, so on, so on, and work out the wavelength of each one, and then link this into the emission line spectra, because you have your lines of your spectra which are equivalent to those transitions. So each the photons in the same spectral line have the same fixed amount of energy unique to that line. The higher the energy photons are found to the right line side of the spectra, and then the low energy photons are found to the left of the line spectra. So it's important to note that if E equals hc over lambda, the greater the energy level difference, the shorter the wavelength. So the largest energy level difference in your atom produces the shortest wavelength. The smaller the energy level difference, the longer the wavelength of the photon emitted or absorbed. So the smallest energy level difference produces the photons of the longest wavelength. So each coloured line in a line emission spectrum corresponds to the wavelength emitted by the source. The photons that produce each line have the same energy unique to the spectral line. Each photon is emitted when an atom de-excites, and an atom only emits particular wavelengths of radiation because the electrons in it can only emit photons with energy equal to the difference between two of its levels. Now, no two elements can produce the same pattern of wavelengths because the arrangement of energy levels in atoms are unique to each element. Now, it's important to note that an absorption spectrum has black lines that arise from only particular wavelengths of light being absorbed by the source, because the electrons can absorb photons with energies equal to the difference between the two levels. So let's now consider the collision of electrons with atoms. So excitation occurs when the electrons move up the energy levels, which can either be given when it receives energy from a photon or receives energy from a collision with another electron. Now, excitation is instantaneous and proof of the particle nature of light. So what can happen is in excitation, the electrons move up energy levels. Now, an ionization is similar to excitation, however, the electron is considered to be free. So in your collision for your ionization, the electron will in fact leave our atom. So you can compare and contrast the two. Now remember, adding electrons makes an atom a negative ion, removing electrons makes an atom a positive ion. So it's important to understand the difference between ionization and excitation. Ionization is caused by the collision of a particle with an atom, normally an electron, okay, and then this gives the electron, or in the nucleus, energy. So the electron colliding with an orbital electron can also cause excitation. Now, the kinetic energy of that first colliding electron is passed on to the second electron inside of the atom, and this causes the second electron inside of the atom to either be excited or ionized. Now, this means that the first electron can actually stop moving. So both ionization and excitation are caused by an atom gaining energy via a collision with the fast moving electron. Now, the fast moving electron is moving in an electrical current. Now, this causes kinetic energy to be transferred from that fast moving electron to the actual atom. Now, the electron can transfer all of its kinetic energy and stop moving, or it could in fact just slow down. Now, the free electron only has to transfer enough kinetic energy in the atom to excite it. This means it could continue to move after its collision. Now, the energy transfer to the atom can also cause this excitation process. So what then happens is the atom will eventually relax and release a photon of energy corresponding to the energy level differences of the two levels. However, the electron here has stopped moving or has at least slowed down, so the current dips if excitation occurs. Now, if the colliding electron does not have enough kinetic energy to cause excitation, it is deflected by the atom with no overall loss of kinetic energy, and an electron absorbs exactly the right amount of energy to move between the two levels after colliding with that free electron. And that contains the same energy or greater energy than that is required to change the levels. Now, as energy is conserved, the energy gained by the electron inside the atom is the energy lost by the electron colliding with the atom. So the free electron's kinetic energy after the collision is the same as it was before, minus the energy transferred, which is equal to the energy level difference inside of the atom. Now, we can also have ionization in collision. Now, this occurs if the fast moving electron transfers enough energy so it moves above the ionization energy of the atom. So in this process, the atom will release an electron due to the ionizing process. So whilst the original electron can stop moving or slow down, another fast moving electron has been released from the atom to replace it. So therefore, the current will stay the same value. Now, in addition, in ionization, the original colliding electron does not have to transfer all of its energy to the atom, so it could be still moving as well. The conservation of energy still applies in this situation. So the idea is any energy above excitation or ionization remains as kinetic energy of the electrons or of the recoiling atom. Now, when an electron collision causes an atom to be ionized, there's no observed dip in the current. Now, in wave-particle duality, we say electromagnetic radiation has a dual nature. It can behave as a wave or a particle. Diffraction and interference, it must be like a wave. Photoelectric effect, it must be like the particle model. So in 1924, Louis de Broglie hypothesized that particles of matter like electrons should have wave properties. In his PhD thesis, he said if wave-like light shows particle properties, then particles like electrons must show wave-like properties. Now, most physicists at the time were not accepting of this theory, but over time his work was evaluated by peer review and his hypothesis was then confirmed by experiments. So this theory has now been accepted to be true unless any new conflicting evidence comes along. So de Broglie's work is an example of how the knowledge and understanding of our nature of matter has changed over time. So all matter can display wave behavior, so has a wavelength called the de Broglie wavelength, which is equal to h over p, the Planck's constant over the momentum. Now, momentum is also written as mv, so you can write it as wavelength is equal to h over mv. That's very, very important. Now, this equation can only be used for matter particles, so therefore it can't be used to work out the wavelength of a wave. Now, the wavelength of the wave wave nature of the particle can determine its properties. The more massive a particle, the smaller its wavelength, which is why we don't observe wave behavior on massive objects such as humans. The faster we move a particle, the smaller its de Broglie wavelength becomes. If a particle is stationary, it exhibits no wave properties. It has a wavelength of 0. If a particle is stationary, it is purely matter. Now, the mass we use in this equation is the overall mass of the particle, the rest mass plus the relativistic mass. Now, all matter has a de Broglie wavelength, which we can use to determine their wave nature. Now, one famous mechanism, which is a wave property only, is diffraction. So it means that if a wave passes through a gap similar in size to its wavelength, it will diffract. Now, in a similar idea, if matter passes through a gap with a gap size similar to the de Broglie wavelength, the matter should then diffract. So you can get an electron diffraction pattern forming on a screen, because in this instance, the electrons have moved through a gap of similar size to the de Broglie wavelength of the particle. So you can get an electron diffraction pattern forming on a screen. So when electrons pass through graphite, they will pass through gaps in graphite similar to their de Broglie wavelength. They'll hit a luminescent screen and produce patterns of rings associated with diffraction. So this was proof that electrons and all particles have a wave-particle duality. The production of rings indicates an interference pattern. Constructive interference takes place where the bright rings form. Destructive interference takes place where the dark rings form. So it's conclusive proof that electrons must be exhibiting wave behavior. If the electrons were exhibiting particle behavior, you would only see a dot. Now, when you carry out this procedure, your velocity of electrons has to be carefully monitored because it can alter the size of your de Broglie wavelength. Now, The diffraction pattern is not observed with humans walking through gaps, as our de Broglie wavelength is much smaller than the gaps we travel through, which is why we don't observe our wave behaviour. But all matter does have a wave nature, and if electrons pass through a gap, such as graphite atoms, the de Broglie wavelength of the electron is similar to the gap size between the graphite atoms, so you will observe this diffraction taking place. So this interference pattern is proof that the electrons have diffracted through that gap size. Now, from the nuclear atomic model, we can then understand why the atom is mostly empty space, because the atom is mostly empty space to fit the wavelengths of the standing electron waves in there. So the atom is mainly empty space because the electrons exist in waves around the nucleus, not as particles, and we need this space to fit in our wave. So the radius of an atom equates to the largest wavelength of the electron in the atom, which can be visualized as the longest wavelengths, as these are the electrons in the highest orbitals. So actually a nucleus is not a an atom is not a nucleus which has energy levels around it. It is in fact a nucleus with a series of electron probability waves existing around it. The electrons form different standing harmonic waves around the nucleus. So let's summarize what we've learned. We should understand threshold frequency, the photon explanation of the threshold frequency, work function, stopping potential, and the photoelectric equation. We should understand ionization, excitation, and understand the idea of ionization, excitation in the fluorescent tube, understand the electron volt, understand line spectra as evidence for the transition between discrete energy levels in atoms, for linking in here with HF equals E1 minus E2, and have an understanding that the electron diffraction suggests that particles possess wave properties, and the photoelectric effect suggests the electromagnetic waves have a particulate nature. You should be able to understand the de Broglie wavelength, which is lambda equals h over mv, where mv is momentum, be able to explain how and why the amount of diffraction changes when the momentum of the particle is changed, have an understanding of how the nature of matter has changed over time, and have an appreciation that such changes need to be evaluated through peer review and validated by the scientific community.